I'm gonna call this talk what it is. This is an emergency talk that's filling in a position that was vacant, and I tried to put this together as much as I could today. This is a talk that I will be giving at Rails Conf later this month, so everyone here gets to be my test audience. This is the rough cut, so bear with me if I happen to mess something up. If you don't know me, I go by Matthew or Goose or Matt. I am Halogen and Toast online everywhere, on Twitter, on GitHub, Cookpad. So if you're looking to get a hold of me, Twitter's a good way. Yeah. The talk that I'm going to give is called Is It Food? A Journey of Minds, Machines, and Meals. So this talk is essentially about machine learning, and I decided I wanted to give this talk because a lot of the talks that I watch on machine learning are either way too high level for me or way too low level. I haven't been able to find that happy medium. And the reason why is because I look at some talks and I see stuff like this, and they start saying terms like linear regression or gradient descent, and I'm lost. Or they start giving a definition of gradient descent, and it looks something like this. Gradient descent is a first-order iterative optimization algorithm to find a local minimum of a function using gradient descent. One step takes proportional to the negative of the gradient, or the approximate gradient of the function at the current point. And I'm lost. I don't understand it. So really, the goals of this talk are to do a few things. I want to introduce machine learning, but in kind of a controlled setting that's maybe a little bit easier. So one of my goals is to make sure that I talk about it from a practical standpoint. I want to give you basically a real-world application of machine learning and kind of talk about it from there. But before I start that, I want to do a brief experiment. I want to find out from the audience what's food and what's not. So let's start with some low-hanging fruit. Is this food?
Yes.
How do we know?
So.
Because it looks delicious.
It's growing on trees.
Because we have the experience.
Yeah, that's exactly right. We have a lot of experience as humans with what this is. We know that this is an apple, and it looks like something that's edible. But this is easy, and it doesn't really get to the meat of our problem. Is this food?
Yes.
But most of this didn't grow on trees, right? But how do we know that this specific thing is food? What if you've never eaten yakitori before? Would you know that this is food?
Maybe so.
Maybe so. I mean, it looks very similar to any other number of dishes or combinations of things. But as a human, we can easily, immediately recognize that that's food. That's pretty sweet, huh? Okay, is this food?
Yeah.
No. It's rubber.
This is the packaging.
So true, it's packaging, but you know, when I look at this, I can kind of see that it has this three-dimensional shape, and in my mind, I know that there's food inside of that packaging, right? So I immediately kind of associate it with food. Whereas if I showed you this, right, you would obviously know that it's not food because there's nothing in there. It's empty. All right, so I have a couple more examples that we need to go through. Is this food?
Yes.
Sure. Is it a picture of food? What about this? I really hope no one said yes. All right, but let's talk about how we are able to identify what's food and what isn't. And a lot of that comes down to our ability to do pattern recognition. As humans, pattern recognition is really responsible for us getting to where we are. It allowed us to develop language and agriculture and a number of other things because we were able to see and identify things quickly. It also allowed us to avoid predators and other things of that nature. So it's something that is inherent to our being. We're exceptionally good at this. But the problem is, if you have a bunch of things, it becomes really menial to say, are all of these 10,000 pictures food? We get bored very easily doing that kind of menial task. And so we want to introduce automation to this problem. So how do we introduce automation to this problem? Well, machine learning is one such answer to solving this kind of problem. And I'm going to narrow it down a little bit into 3 different types of machine learning. I'm going to call it unsupervised, supervised, and reinforcement. And I just kind of want to introduce them, again, in narrow scopes. So if we talk about unsupervised learning, that's where we just say, computer, here's some data, and kind of figure out, groups. I'm not going to tell you what anything means. I want you to divine information from it, right? Which is very different than from supervised. In supervised learning, we tell it, here's a bunch of information to train you up and tell you this is this and this is this. And then later on, we can provide it with new examples and give us information. And then reinforcement is kind of like supervised, except there's a carrot that we keep feeding it every time it gets something right. So as it learns new things, we keep telling it, good job, good job, good job, and it uses that information to apply to the next iteration. But really, I want to focus just on supervised here. And the reason why is because I want to talk about neural networks. So I'm going to give you a brief history of neural networks, or specifically artificial neural networks. So the first one was actually built in 1957, called the perceptron. And this is really interesting because I didn't imagine that neural networks went back this far in computing, but to be honest, it went on for quite a while until about 1969 or so, when they realized that computers were just too slow and unable to handle it, and there was a specific thing they couldn't implement called exclusive OR, but we won't worry about that. So in this issue, I'm going to fast forward quite a bit to TensorFlow in 2015. It's a huge jump, again, brief history. So TensorFlow is this library that's kind of come into existence and has helped make, at least to me, machine learning more popular and more accessible. So let's talk about what TensorFlow is. TensorFlow is basically a program that operates using a data flow graph. It might look something like this. Each layer in this graph takes in a tensor and returns a tensor. So the tensor that comes out has some operation that's performed on it. And you can run these operations on your GPU to make it really, really fast. But I just said tensor. What is a tensor, right? Well, if you look up tensor, you get an image like this, and then you just assume that you will never, ever know what a tensor is. But the actual answer is that a tensor is just an n-dimensional array. We don't know how many values. It just depends on what's going in and what's coming out. So it could be a 3x3 array. It could be a 1x1 array. We just have these arrays of information that go in, have some operation performed on them, and they come out. So if we go back to this, and I'll cover what inception v3 is in just a second, we basically have a tensor come into the starting point, it goes all the way through this thing, and then comes out the end, and we get an answer to some question that we've asked. So what is inception? Typo. Need to fix that. So inception v3 is actually made by Google in order to do image classification. And actually, it operated originally on this set of data from ImageNet, which is just a huge number of images that have been hand-tagged by humans to say what things are, so that we can test machines against that data to determine how close we can get. And in 2015, TensorFlow did a really great job and became part of the public. So we can use this kind of a solution of having these tensors perform operations to determine if something is food using TensorFlow and specifically using inception v3 with it. So let's go back to my initial question. Is it food? So why am I asking this question in the first place? And the answer is that I work for a company called Cookpad. And one of the things that we have a lot of are images of recipes. But we want to make sure that we're getting images of recipes, things that people have actually cooked. And there are a few things that we don't want to have appear on our websites, like people. We definitely do not want people on our website at all. And the reason why is because we want to protect the privacy of our users, and at the same time, there's no reason to have them in the photo. You know, there are other situations that pop up too that we definitely don't want appearing on the website, so we need to take those into consideration as well as we are getting things uploaded, because if we immediately publish those to your feed, you might be upset, and we don't want that. So I'm going to take this problem and try to apply it to building a Rails application around this. I made a bunch of mistakes in this process, and I don't want you to make the same mistakes. So let's start with mistake number 1. I use OSX. The reason why this is a problem is that none of the tooling that's built is built around Clang, which happens to be your compiler on OSX. A lot of it's built around GHC. I don't want to get into the nitty-gritty details of that, but it is infuriating when things do not work and you have seg faults, which is what happened to me more often than not. So that was a little bit disappointing. You could try not to use OSX, but I still ended up using it, and I'll get into why a little bit later. Mistake number 2. I went into this as a Ruby developer, and I said, no Python. None. I'm out. We're going to do this all in Ruby. And interestingly enough, there is a Ruby library written for TensorFlow that's released by Semantic called tensorflow.rb. Okay, that did not work for me for a number of reasons, which I'll get into. Mistake number 3 is that I couldn't get the tensorflow.rb bindings to work on my local machine because of compiling, and they suggested using a Docker image. This was mistake number 3 because my experiences with Docker usually turn into this. Time after time, I would just keep running out of room on my machine, and I would have to free up space, free up space, free up space, and then you have to manage all this. And I really don't like managing Docker images locally on my machine, so I kind of went a roundabout way. So let's talk about my road to success here, because I did get this working to some definition of working. Quick note, your mileage may vary. I don't know how your system's going to deal with compiling or anything else, so I tried to come up with what I consider the easiest path, and we'll go from there. So, installation. We want to set up TensorFlow, and we want to set up it to work on our machine. And the answer was to use Python. I really fought against this tooth and nail, and after error, I just gave up. Even with the Docker images, I was still getting compilation errors, and I'm not sure why. The nice thing about using Python in this situation is the tooling for this is fantastic. It just works. There are people who are really into this kind of stuff, making sure this works everywhere. That's not to say as a Ruby community we shouldn't be trying to get the library to work in Ruby. It's just that if this is your first introduction to it, you're going to have a much easier time if you just start with Python and use it, because it's pretty much guaranteed to work. So I don't want to advocate this as a no Ruby, just your first step shouldn't be in Ruby. It should be in Python or something else that it works really well in. So the basic steps that I took to get it working were to install Python, to install virtual env, to set up a virtual env in some directory, and then to do source bin activate, which basically, it's kind of like a sandbox for your dependencies. So I've set this up, and now I want to focus on Inception was designed for that specific image set that I told you about before, right, from ImageNet. Most of those pictures aren't food, so this isn't going to help me. I can't use that to get food. So in order to set this up, I want to basically do what's called retraining, or more specifically, I want to do transfer learning. And transfer learning is basically where if you've already trained it most of the way, you can build upon what you've already trained it on and just add another layer. So in order to do this, I'm going to need lots and lots of images of food. So I created a directory called data, and then I started collecting what I wanted to have inside of here. Now this is really important. Collecting your data is critical, because there's a few things you need. You not only need good examples of what is food, you have to have good examples of what isn't food. If all you've ever seen in your entire life is food, everything's food. So we made sure that we created some situations that we wanted to look out for. Specifically, we didn't want people, right? So I created a category for people, and we didn't want text. There's a little sneak that people try to do in our application where they'll put a URL in their image to try and direct people out of the website. We don't want that happening. So actually detecting not only is it food, but is it food with text? That's bad. So we basically use this data set to train it, and there are tons and tons of images that are basically inside of these directories. There's really no easy way to do this process. You have to manually go out and get a bunch of images to train with. Now, the images don't have to be very big because TensorFlow doesn't operate on big images. It only operates on 299 by 299 pixels. So you don't really need big images, you just need lots and lots of small images. And if you have bigger images, it's going to resize them down. So if you want to speed things up, you can just batch process them and resize them yourself so that TensorFlow doesn't have to do that. Sorry, ImageNet doesn't have to do that. So I gathered up all my images, and then I wanted to retrain. And the easiest way to retrain was just to grab the Python script that they already have available for me, and I changed a few things inside of it so that it would output the results to my local directory rather than to temp. And then I just ran this function. And after you run that function, you wait. And wait. And wait. And wait. And it looks something like this. It's going to go through and say, it's creating all these bottlenecks. And the first time I saw this, I was like, what is a bottleneck? That sounds interesting. And actually, a bottleneck is an informal term to refer to whatever the output was in the previous layer. So when I said we were retraining the TensorFlow, we basically take that last layer, which says, this is one of these images, and we pop it off. And we're going to put on a new layer. But we need to reuse all of those images many, many times in order to determine what our final output is. So if we can just do that once for each image and cache it, then we don't have to do it again. So what this does is it creates a ton of files in your temp directory so that it doesn't have to keep running through the entire ImageNet inception every single time. And then after it gets done making all of these files, and by the way, this was nice and fast because I had already run this once. If you haven't run this, you're going to see it printing out every single image saying it's creating a bottleneck for them. After you get through that, you'll see something like this. And this is where it actually starts training. I'll briefly look at the script that I downloaded, but there isn't much point going into it because it's highly technical. And I'm trying to avoid technical things. The thing I noticed here that was kind of interesting to me is that they keep repeating the three things: validation accuracy, train accuracy, and cross entropy. And this is actually really interesting to me. This script automatically takes all of your images and partitions them into different sets of data. One is going to be your training data, one is going to be your validation data, and one is going to be your testing. And it basically uses these sets of images to ensure that every time it makes a change to itself, that it's trying to minimize the cross entropy. It wants to get that number as low as possible. And that basically means that every change you make is meaningful, that it was able to find new information or better detect images, and that it wasn't ruining itself. So typically when you're training a system like this, you want some loss metric. And this automatically did it for me, so I didn't have to worry about that. The output of this is two things. A graph. Remember I mentioned that for TensorFlow to work, we need a data flow graph, all the steps. We get a new graph that has our image set at the end, so it knows how to identify those things. However, it only identifies those things into numeric buckets. Bucket 1, 2, 3, 4, 5, etc. So the other output is a file called labels, which just has the text translation for what those things are: person, food, text, etc. All right, so let's use this and try and see what that looks like. So I wanted to label an image, and actually I found it easy just to copy the code from this URL and make a label image.py. So inside of that file, I just changed it to use my local directory for the graph and the labels. So let's see that work real quick. So I'm going to activate virtual env, and then I have a few pictures in here. Test 1, which is some food. Looks like that. That's a sushi pizza from America. Don't ever eat that.
This is not food.
It is food, unfortunately. All right, so we want to verify that it's food. So I'm going to run Python label image and pass it test1. And it's going to print out a bunch of warnings that I'm not going to care about. And then at the end, it basically assigns scores to each of the different categories. Now, all those numbers have to add up to 100%. And this is basically how confident it is that each thing kind of falls into each bucket. And you will never get 100% unless you only have one thing in your system. So you should never aim for 100%, right? The idea is that this is never going to be 100% accurate. You have to work within some amount of variability. So here, it was, about 93% sure that was food, and that's good enough for me. I'm good with 93% sure it's food in order to decide what to do. But let's take a quick look at what that script did. And I am not a Python programmer, so if I say something that's completely wrong, I apologize. So actually, this script isn't that long. It's only 32 lines because most of the work has been done for us with the retrain script. Mainly, we just create a TensorFlow session, and then we get the softmax tensor. The softmax tensor is what chose which group it went into and gave it some percent. And you can see, actually, what we do is we say, graph get tensor by name, final result, right? That's actually referring to, if you remember the picture of inception going all the way down the chain, that's the last part of that chain, is the final result. So we want to basically get that part and then run our images through that in order to find out what they are. So you have to go through this song and dance of saying, okay, I'm going to run my image data through the softmax tensor and get some predictions. And then we want a certain number of predictions from the top. This Python code's a little weird. I think they intended you to be able to change this to whatever number you wanted. As far as I know, that takes an array and then returns an array with the same exact elements in it. Because it starts from negative the length. And then it reverses the array so that they're in descending order. And after that, we just go through and we say, okay, we need to get the specific label, because it's, again, 0, 1, 2, 3 are the buckets that it put it into. We read our label file and then get the specific label. We get the score and print it out. So that's basically it for labeling the image. I don't think I could have written this myself off the top of my head, so I definitely suggest just going out online and finding it. There are a few different tweaks you could probably make to this to make it more accurate, but this was simple enough to solve our problem. Okay, so back to mistake number 1, and that was that I was using OS X and things didn't work, but I wanted this to run on my machine, and I wanted it to basically be usable in a Rails app, but I couldn't compile anything. I could get it working in Python, but I couldn't get it working in Rails. So how do I solve this problem? The answer for me was kind of make a web server. But instead of making a Rails web server, I was just going to make a Python web server, and that would be a service that did exactly what I wanted it to do. So I installed Flask, which is kind of like Sinatra, but for Python. And then I just took that label image.py and turned it into a small server that did what I wanted it to do. So let's use that real quick. Okay, so this is just my small Flask server. I basically took the code that I had before and gave it a route called classify. And it basically just reads those predictions and returns them. So it's not really that complex. So on top of this, I just built a Rails app that calls out to this to get the results. So let's see what that looks like. This is actually my Rails app. I choose a photo, pizza, and hit classify, and it says it's food. Yay! All right, let's try some dirt. Not food. Good job, application. So yeah, it didn't have to be more difficult than that.
Try the baby taco.
I'm sure that would work, but I don't actually have a reference to that image. Hold on 1 second. We can do this.
Yeah.
Sure. Where are you hiding, baby taco? All right, here we go. I don't want to know.
Imagine.
All right, so let's get baby taco. Please don't say it's food. Please don't say it's food. Oh. I wonder if my server failed. Invalid argument error. Invalid JPEG data size. Oh, because it's a PNG. Curses. We can fix this problem. Yeah. Wait, can I save this as a PNG from here?
Export.
Export. Change this to JPEG. Make sure I select the right one. Thank you, OSX. JPEG. Great. Alright, moment of truth. No! Our machine overlords have succeeded. Alright, so that was the end. We got it working. So basically, I wanted to point out that in my heart, I feel like I'm a Ruby programmer, and I wanted to avoid other things, and it was a mistake. You shouldn't, at least for getting started. If you want to contribute to the machine learning side, it clearly needs some help from the community. I don't feel like there's enough people contributing to it to make it foolproof, and it would be really great if we could, because I would love to be able to do this in just Ruby and not have to use Python. But it was really fun to see this example working, and I could really train it with any set of images that I want. So I felt like that was a good introduction, so I feel like I'm kind of ready now to find out what the next step is, and to actually kind of learn what some of the terms are that apply to what I was doing. But I'm not there yet. So that journey is to be continued. Here are the image attributions for the things that I used as images. And again, I'm Goose at those places. Now, real quick, last time I cold called everybody with an email saying, please fill out a survey. I don't like sending unsolicited emails, so instead, if you can please take out the time to fill out the survey, we can use the information you provide us to try and make the event better. So your feedback is greatly appreciated in making this event better and finding new ways to improve the community. Thank you, everyone. Are there questions? Yes.
Yeah, you gave the example if you want to be able to classify pictures of food with text there. So I'm just wanting to understand how it works, because you said everything has to be fitted into one specific category with some percentage assigned to it. So if something had any text in it, then it would be like 90% text? Or how does that work?
So, one thing, this is not the code we're actually using on Cookpad. We do have code that does this, but I was trying to start from scratch. The idea, right, is to have really good images in your example data set that kind of cover those cases, and you try to get it to that point. So, let me see. We go to data. I don't actually think any of these have food in them, so I'm not quite sure. But we have lots and lots of examples of text. I'm guessing specifically, there's probably a way to weight these things. I'm not sure, but
I guess you could also like do multiple classification processes, like is this food or not, and then is this text or not?
right. So one of the things that could happen, right, is that it looks at an image and there's both text and food in there, and so it's not sure and says, okay, 40% it's food, 40% it's text, and some other small percent it's something else. And in general, what we're looking for is some bar to determine is it food or not. So if it's not, I think what worked for me on mine was about 85% or higher was usually what food fell into. But I think the actual code that we're using is like 90%. So it's actually a bit more accurate in determining what's food. So if there was text on there, I'm assuming it would actually say like, it's in between these two things. It's both food and this other thing, and we don't want that. So you're looking for a high percentage value to guarantee that this is mostly just food.
I see. And then I gather, like, if it fails your test, then you're flagging it and manually going through it, or what happens next?
Yeah, so actually, there's a whole system of things that we flag things for, and that's one of the things that, yeah, it would get flagged and then have to be reviewed by a moderator. But, you know, we can eliminate having to moderate all of the images and only have to moderate some. So yeah, that's basically that.
You retrained the network on your MacBook?
Yes,
And how long did that take?
about 30 minutes.
Oh.
It's actually surprisingly fast now, and that's not even using the GPU, because I don't have an NVIDIA card on here as far as I know. But if you have an NVIDIA card, you can actually set up TensorFlow to use the GPU, and it goes much, much faster. So yeah, it was surprisingly fast for going through all of this.
And how many images do you have in your data set?
I don't remember. Let's see. So it's only about 1,800 here in food. There's lots of flowers because there's actually a flower data. Oh, it's only 342. There's a data set of flowers. Apparently, we trained with that. What's in here? Another 1,119 for things categorized as other. People were almost 1,700, and text, I don't think it's that many. So about 668. So I think there's around, is that 3,000 to 4,000 images that I was training with?
I think it seems like the retraining is really successful. Like the pre-train is giving you really good results. You just need a small tweak to get this
Yeah, so
specific case.
right. So the original data set for ImageNet was to take images and categorize them into 1,000 different categories. And so all of the steps before were guaranteed to kind of be able to do that, and we only cared about the last step in determining, I forget what they're called, but basically you get all these traits that are essentially passed down to you at the end, and what you want to do is then take those traits and decide, this trait strongly implies that it's this, and this one this. And so if we can just retrain it, so we already have all the traits, and we say, these traits kind of mean this, this, and this, then only the last layer has to change, which is really effective, because if we had to change the whole thing, it would take forever. Did you have a question?
Yes. Would make sense to use production data to train the network? Because I guess that you get lots of images from users and you manually label these images. Isn't that data really useful?
Yeah. I mean, my image training set didn't have it because I can't take images from there and show them publicly here. Because they're not my images. But yeah, essentially, if you can actually use real data that's already been verified, we have tons and tons of images that we can use for that purpose.
Like
so
retrain the. So I guess you have moderators. So the
yes.
action of the moderator retrains the networks.
No. So we have our model and it's set. We don't actually have that reinforcement learning set up. So if we want to retrain the model, we have to manually go and retrain the model. It's the supervised learning, not the reinforcement learning that we're doing. There is the possibility of doing that, but what we found is we don't really need to because it hasn't really gotten things wrong yet. So within like a high amount of certainty, we can say, this is food. And I think, I forget, I don't want to quote them, but there's like precision and accuracy, and those values are really high for our data sets. And those are important somehow. Yes.
Yeah, so I remember when I used to work here. Of course, you know, it was way before this whole thing was like machine learning and whatever. And I remember like one case that you mentioned that at Cookpad, you know, you don't want to have users to post pictures of people or not safe for work, whatever. And there was one case that was also something that I saw happening, is that some user would post actually a picture of food, but it was just like an apple, you know. It was like, I made a recipe, it's an apple. And ingredients, apple. Cut it, eat, done, you know. And it was, you know, most likely some, I don't know, high schooler and just say, hey, check out my recipe. And it was like training on Twitter as a, anyway, ha ha ha, you know. And it was something that support had to deal with, you know. And how do you go from there, you know, like, of course you can train your model to have like raw food images, but then sometimes that could be a recipe that's, you know, like actually legit, because it just happens to look like, I don't know, the guy makes a bento and it's shaped like an apple because of cake, you know, fantasy cake, whatever. So yeah, I was wondering, you know, if you already guys had to tackle those cases where it's actual food in there, but it's not a recipe.
Okay, so we're not, as far as I know, tackling that specific problem yet. But the idea, right, is that you don't have to use the same process. We can have another process that identifies what ingredients does it look like are in this recipe. That's not necessarily going to be perfect, but we could say like, oh, it only looks like there's an apple inside this recipe. And if there's only one ingredient, that could be a red flag. So things like that could pop up. And we might not say like, don't let them post it. We would just post it and be flagged, and then someone could take a look at it later on and say, oh, clearly this is just an apple. But that's a general idea. I mean, the idea, right, is that there's so much valuable data here that we can extrapolate information. And so if we can do further things like, oh yeah, we can tell that you have these ingredients in the picture, oh, but maybe you didn't list it in the list of ingredients. Like, we can help authors be able to make better recipes so that they don't have those types of mistakes. But that's to be continued. Like, a lot of those problems aren't easy yet, and we're kind of exploring how to do those things in different ways. Anybody else? All right. Thank you for bearing with me on this rough cut talk. I hope you enjoyed it. Please don't make me talk next month. I really, 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 really want volunteers. So even if you have just an inkling of something that you want to maybe talk about, you can bring it up to me. I can maybe offer ideas or pointers or somehow convince you that it's the right thing to do to come next month and give a talk. My backlog of speakers looks like this, so I want to fix that problem. So if you're at all interested, please, 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 the community needs you. Okay. Thank you very much, everyone.